talks and discussions, and but earlier we never thought about that even.
No, no. Let's see. Yep. So what's the weather like in Guwahati?
It's not that cold. Now it's around 20 to 22 degrees Celsius.
Yeah, that's not so cold.
Uh,
That's the dream temperature for us here in the summer.
yeah.
So, Professor Hansen, so we just wait 1 or 2 more minutes and then we will begin.
Sure, yes.
Okay. So, Professor Santra, so can we begin?
Sure, sure.
Okay. Okay. So, good evening. Welcome to our next round of physics colloquium. So, we are very happy that we have today with us Professor Alex Hansen from Norwegian University of Science and Technology. So, he is a very well-known figure in his field of research. So, let me have a brief introduction of Professor Hansen. So, Professor Hansen has completed his PhD from University of Rennes in France in 1986. Then he has done a couple of postdoctoral positions, one from starting from 1896, 1986, one in France. Then he moved to Cologne in Germany in 1987. Then in 1988, he moved to IBM Bergen Scientific Center, Norway. Then he has done another postdoc for 2 years in the Department of Physics, University of Oslo, Norway. Then he has taken a permanent position in 1991 to 1993 from CNRS in France. Then in 1994, since 1994, he has been working as a professor in NTNU, that is the University, Norwegian University of Science and Technology, Norway. So coming to his significant awards and fellowships, he is also in 2009 he has secured this honoris doctor honoris causa from University of Rennes in France. And in 1981 to 1982, he is a NATO Science Fellowship, Norway. And in 1986 to 1987, he is a Joliet Curie Fellowship, Saclay, France. And there are many other awards which I cannot mention. His list is quite big. Okay, so then one of his very exhaustive research activities is that thing. He is a field chief editor of Frontiers in Physics. Starting from 2013 and from 2017, he is the editorial board member of International Journal of Modern Physics C, and from 2006 onwards, he is the editorial board member of European Journal of Physics. And he is also a significant body member of this elected membership in Norwegian Academy of Technical Sciences from 2002, and in 2003 is also elected membership of in Royal Norwegian Science of Society of Science and Letters. Okay, so then in 2000 he is a member of European Physical Society. He has authored hundreds of scientific research articles. The number amounts to about 271 with about thousands of citations. So it is we are very happy to have him. If I'm not wrong, he is also author of the it's a book or the volume that is the Physics of Porous Media, okay, which is a very recent one. I think this is very good for the people who are working in this area. So with this brief introduction, okay, I welcome Professor Hansen to deliver his talk on the statistical mechanics flow of porous media.
Okay.
Professor Hansen, please. Yeah.
Thank you for this kind introduction. And what I'm going to is something I've been working on for quite some time now, and I'm going to perhaps apologize a little bit because you're going to see a number of equations. It's just unavoidable. But anyway, so here we go. Let me just get the right laser pointer. Okay, so first of all, so here are my collaborators on this project. So Erik Rudflekke, he's a professor in Oslo, colleague. Husan Aifin is a graduate student, Håkon Pedersen, a graduate student, Subhadeep Roy. He was a postdoc with me, and he's now back in India, but will go to Manchester quite soon. And Per Anders Slotte, he's a researcher with us. And then I should mention actually my closest collaborator, Santanu Sinha, and he has his PhD from Professor Santra at IITG. And we are starting a collaboration with the first meeting tomorrow, actually. So we are very much looking forward to this. Anyway, so let me start with on the science part here. And let me take a step back and be a little bit philosophical. Let me go back to a paper that was published in 1972 by Phil Anderson. And Phil Anderson, that's Anderson localization Anderson. I mean, he is one of the great condensed matter physicists. And in 1972, he wrote this very, very important article, More is Different. And that was a result of him being very annoyed at what he felt was the arrogance from the high energy physicists. And here he writes, it seems inevitable to go on uncritically to what appears at first sight to be an obvious corollary of reductionism. And here it comes, if everything obeys the same fundamental laws, then only scientists who are studying anything really fundamental are those who are working on those laws. And of course, this was a source of his irritation because high energy physics, that's sort of the most fundamental thing you can think of, right? And that means that what he was working on would not be fundamental. But here's what he says. The main fallacy in this kind of thinking is that the reductionist hypothesis does not by any means imply a constructionist one. Namely, and here is the essence, the ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe. You can't go the other way, he says. Namely, the constructionist hypothesis breaks down when confronted with the twin difficulties of scale and complexity. The behavior of large and complex aggregates of elementary particles, it turns out, is not to be understood in terms of simple extrapolations of the properties of a few particles. Instead, and this is the reason why I'm discussing this sentence, at each level of complexity, entirely new properties appear, and the understanding of the new behaviors requires research that I think is as fundamental in its nature as any other. So what he's saying is that you have elementary particle physics, fine, that's a fundamental science, but chemistry is also a fundamental science, because chemistry is the description of phenomena at that scale. I mean, you can't get far in chemistry if you are looking at elementary particles. You start with the quarks and so forth. You just can't do it. I mean, this is a different level. It requires a different way of thinking, a different way of set of variables, etc. So they're all fundamental, but they're fundamental at different levels. You should see nature as a series of different scales, and each scale should have its own description. So let's now try to tie this in with porous media. So this is a picture from 2020, and it's a picture of nano-sized particles, and what you see here are the individual atoms here. So this is basically as far as we can get without, doing high energy physics. But at the same time, here's a piece of solid silicon. And the point now is that the properties of atoms, even the properties of atoms in assemblies as the one you see to the left here, this one here, and what you see here, where you have 10 to the 23 atoms, you don't get very far describing the behavior of this block here by thinking atoms. You should think at this scale here. So if you think like this, at this scale where you can see a block like this, you can talk about solids. And solids, they are at this scale described by the theory of elasticity. You have other things, of course, how temperature behaves, how that spreads out and so forth. But basically, you have continuum equations that describe the behavior of this block. And there's not a trace of atoms in that description. Then you have the gases. That's not a state of matter, right? How do you describe that? Well, you do fluid dynamics. It's yet a third state of matter. Describe them also with fluid dynamics. Basically the same kind of theories adapted for them. And here comes the point. Now let's look at porous media. A porous medium, that's a material that has holes in it. And if it's going to be interesting, the holes are in contact with each other and you can send liquids through that. That's a porous medium. And the liquid flowing, that's porous media flow, and that's what we're going to be interested in. And here you can see a computer simulation of the behavior of two immiscible fluids inside the porous medium. The porous medium, you can sort of see two cuts through it here and here. And then one of the liquids is made transparent, the other one is red. So see here how the flow is appearing, and it's this sort of complicated cloud, but I can assure that's a highly, highly correlated behavior with lots and lots of structure. But here's a photograph of a wet concrete floor. What has happened here is that the concrete has been in contact with the ground below and water has seeped through it. Now, concrete is a material which is a porous medium also. And the pores here are also in a nanoscale. They're a little bit bigger than atoms, but not enormously much bigger. So it's a nanoporous medium, and you have this flow through. Now, at this scale here, you don't see the pores at all. So you have the properties of pores here, and actually the state of the art in porous media is that we are really beginning to understand what is happening at this level here. But then you have the behavior of porous media at larger scales, at what you could call the continuum scale, where the pores are so small that you basically cannot, they are irrelevant. It's like a block of solid compared to atoms. And the big question is, how do you describe this? Let's say it this way. You had solids, theory of elasticity, gas, fluid dynamics, liquids, fluid dynamics, porous media, but here's where we are. We don't have anything. Well, we have an old theory from the 1930s that people are using, and but everybody knows that this is not. It's just an approximation. It is just hand waving. I'm not going to go into what it is, but that's what people use. And the question is, we need a precise, good description at the continuum level of porous media that matches elasticity and fluid dynamics. So we are in some sense trying to now construct a theory at the level, large scale level, where the porous medium is a continuum. And we basically have to start from scratch because it really doesn't exist anything at the moment which is usable at this scale. All right, so let's now get into porous media, the theory here. And let me start by defining what is we call steady state flow. So here's a machine. Now this block here, this square, that is actually two glass plates that are placed against each other so that you have a two-dimensional space between them. And in this space, you have glass beads who are held in place by glue. That produces a two-dimensional porous medium. And you're injecting two liquids here, which are immiscible. They don't mix. Actually, it's air and it is a water glycerol mixture, and that is colored black by essentially ink. And you are pushing this into this porous medium at the same size time. And they will then mix and produce an area here where we have steady state. And this is what it looks like when you start this experiment. So you fill it completely with the water glycerol mixture, which is basically black here. You see it's still grainy, but that's because of the glass beads. And then you start pushing in this mixture. And this is as it progresses. So this is after a little while, longer. Here you are in the steady state. And this is what it looks like on the computer simulation. The same thing. This is a simulation done by Santanu, Sinja. And you see from the left here, the liquids are injected and you see how it evolves. And all right, so now we are in a steady state. That's what you're going to concentrate on now as we go along. This is equivalent in terms of thermodynamics. This would be, or statistical mechanics, this would be equilibrium state. It's a steady state. You see, it's just driven by fluctuations. There's no structure beyond fluctuations here. All right, so steady state is when the macroscopic system parameters remain constant or fluctuate around well-defined averages. And we wish to construct a statistical mechanics now for steady state flow. And if you say statistical mechanics, when you go to a continuum limit, you will usually get to thermodynamics, but in our case, we will call it Euler theory. And before I now get to this Euler theory I'm going to describe for you, I just need to define a few things. So here, the first thing is what we call the representative elementary area. And let me represent it this way. This thing here, this box, it's not a box, it's a porous medium, right? The whole thing. And these blue arrows, that is indicating now that there's a flow through the porous medium. This little thing here, that's a little area I've cut. And this area is orthogonal to the average flow direction. This is what I call a representative elementary area. You know, usually you will see representative elementary volume. That's what people discuss usually, but we need an area, not a volume here. And you'll understand why in a little while. Now here's how I've taken out that little thing. Let me see here that I take this thing here out, sorry, and here it is. It has an area A. There's a porosity. That's the fraction, volume fraction, which is not covered by the matrix phi. Multiply them and get the area which is not covered by the matrix, that is the transversal pore area. And here's what we send through this representative elementary area. That's a total volumetric flow rate. That's the volume per time that goes through here. That you can divide up in two different liquids moving at the same time here. It's a wetting liquid and a non-wetting liquid. And that's the volumetric flow rate of the wetting liquid, and that's the volumetric flow rate of the non-wetting liquid. You sum them and you get the total volumetric flow rate. Now, this area here, pore area, you can divide into two parts. It's the one which is covered by the wetting liquid, another part which is covered by the non-wetting liquid. So these are two parameters, both scales with the size of this rev at the same time that characterize what happens here inside. And now I can divide out, I can define an average wetting velocity. That's the velocity of the wetting liquid. So that's the volumetric flow rate of the wetting liquid divided by the area of the wetting liquid, and the non-wetting corresponding non-wetting. And the fraction of the area which is covered by the wetting liquid compared to the total pore area along the cut. That's the wetting saturation and the non-wetting saturation. And I can take this Q here divided by the total volume metric flow rate divided by the area, and I get the average velocity through the system, irrespective of liquid. And if I now combine this definition here with this sum here, and the average velocity, I mean the velocity of each fluid and the saturations, I get this expression here for the average velocity. All right, so now I come to Euler theory. This we published in 2018. And that basically says that the volumetric flow rate through this area, if I change the area, let me go back. If I change this here, I make it a little bit bigger, what happens to the volumetric flow rate? Well, if the change in area is a lambda, well, then the flow rate goes up by lambda. Now, if I take the derivative on both sides of this equation here and set lambda equals to 1, I end up with this expression here. And that's the Euler theorem for homogeneous functions of the first kind. And if you now look, this quantity here and this quantity here has the dimensions of velocity. So I can call them velocities, but let me put a hat over them. So I have Q, the total volumetric flow rate is this areas times this and this. And I already had this expression here. That's what I just told you about from the preliminaries. So then it would be perhaps obvious that this is equal to this and this is equal to that, but that's not true. The most general relation between the velocity of the wetting liquid and the thermodynamic velocity of the wetting liquid is as you can add something. And that something has to have this form here. It's a function times the non-wetting saturation here and the wetting saturation here. If you plug this in here, you see that this extra term cancels. And this we call, this is a new velocity we call the co-moving velocity. Now I'm going to skip some derivations here, but we can actually express the the thermodynamic wetting velocity and the thermodynamic non-wetting velocity in terms of the average velocity and its derivative like this. This is an equation that follows from what we have here. And now if I combine this with the co-moving velocity, I actually end up with having the wetting velocity and the non-wetting velocity. These are the physical velocities, not thermodynamic velocities, which are difficult to observe. These are real physical velocities. And I now actually been able to express them in terms of the average velocity and this co-moving velocity. I can turn them into vectors so that I actually can do calculations with them, in terms of flow. I can combine them with mass conservation and incompressibility, and that gives me two equations. This is the incompressibility of the two liquids, and this is the compressibility of each of the liquids. I get these two equations here. If I now add on a constitutive equation for the average velocity, that will depend on gradients in pressure and gradients in saturation. And I add on a constitutive equation for the co-moving velocity. And it turns out, and this is quite amazing, it's a very simple function, the co-moving velocity. I mean, we have looked at experimental data in tons and tons of experimental data and computational data from Santaner's Senior's model and from using lattice Boltzmann and so forth, and we always find it has this form here. It is, yeah, it seems quite universal, and we don't understand why. But I'm going to get a little bit closer to why, a little, sort of a halfway why a little bit later on. But anyway, so this is co-moving velocity. And just to demonstrate that we can do calculations with it, this is a drainage experiment done computationally. We are now starting out with a wetting liquid here, and we're starting injecting a non-wetting liquid here. And we basically see now viscous fingers are appearing like this. These are equipotential lines for the viscous fingers. So you can do calculations with this. It's a complete set of equations, but we would like to do much more than this. If you look at very carefully what this Euler theory is based on, how it is put together, it is very, very close to what you would do in thermodynamics, and it's some sort of a thermodynamics. And then the question is, if this is some sort of thermodynamics, does there exist some sort of a statistical mechanics beneath this? Statistical mechanics that can sort of make the link between the pore level and what we see at this continuum level. And if we go back to what Phil Anderson says, basically that's a very important goal in science, actually, to find connections between these levels of description. And that's how one should think of this. Here's a gas in 2 dimensions. So these ink spots here, they are actually molecules or whatever, and they bounce around because this is a gas, given temperature and so forth. And this is a typical thing you would consider in statistical mechanics. But let's draw the space-time diagram. So here is now this little 2-dimensional thing. It's drawn here as this square, and here are the particles, and these are the world lines of each of the particles. So in reality, what you're dealing with here is a cut through this weave here of threads, and each thread is the motion of a particle in space-time. Now, if you think about it, here is a core sample. So this is a porous medium, and a standard experiment you do is you inject the 2 immiscible liquids inside here, and they pass through the system like this. And you inject them at the same time, you get into this steady state. And what do you see? These are cuts through the core at different times, and not at different positions here, like this. So this, for example, here is a core, I don't know, it could be from here. It's cut through here. And you see the matrix, and you see the black liquid, and you see the white liquid here at the same time. And here's how you should think about it. These are like, you know, snapshots of a two-dimensional gas like this. And here are the world lines, the space-time diagram, and it is essentially like a core. But of course, the oil spots here are not in, as you move along here, they are clusters of finer size, so they're not elongated lines like this. But the analogy, what you should think of here is that you can actually try to make a statistical mechanics of what's happening in these cuts here. And then the third direction, the flow direction, that's actually like a time direction. Okay. So here's again the representative elementary area. There's a pore area, AP. And here's the Z direction where the flow is moving in this direction here. That acts as a time axis. And you have a statistical equilibrium in this here, because this is the motion direction of the motion. There are no driving forces in this plane here when we have set saturation gradients to 0. So you would expect a equilibrium. And that means you can now try to construct a statistical mechanics where an equilibrium statistical mechanics of what's happening in this plane here. And of course, as you move upwards, you're going through different configurations, and that's what you do in statistical mechanics also. That's the, that's the essence of it. Now, how do you do that? If you try to actually go from fluid mechanics to construct something like this is extremely difficult. I've really tried as hard as I can, but it is very, very difficult. However, there's a much nicer, more general way of doing statistical mechanics, and that's called Jane statistical mechanics. So let me just describe this to you quite I mean, a little bit stenographically. It's a generalization of the Laplace principle of insufficient reason. And what Laplace said is that two events are to be assigned equal probabilities if there's no reason to think otherwise. What does that mean? That means that if you know nothing about the system that has two outcomes, the best strategy is to give them equal probabilities. Now, and this is very, very important. So in 1948, Shannon tried to say the essence of Laplace is to say that if you don't know anything about your system, best strategy is to say that the probabilities are equal. That you can generalize to n outcomes. So if your system has n outcomes, if you don't know anything about the system, well, the best strategy is to set them all equal. The probability should then be 1 over n for each of them. And then Shannon said, okay, so let's see, can we make a quantity that is an expression of what we don't know about the system? Can we quantify this? And he found that it has to, such a quantity has to obey a certain principles. For example, if you now divide you have a system with different parts, you divide them up into different classes and look at the probabilities of these classes and so forth, and say that it should be invariant under this and you know, under increase of the system size, etc., etc. When you do that, all the symmetry principles you put in, you end up with this as the quantitative measure of what you don't know about the system. And this is the Shannon entropy from 1948. And in the late 50s, Janes went further and constructed a generalized statistical mechanics for information theory based on the Laplace principle that says, once again, two events are to be signed, the equal probabilities if there are no reason to think otherwise. And here's how it works. So here is the entropy, PIs, and you don't know the P's. But what you know about the system is, first of all, what outcomes you can have. And then in addition, you can have a number of quantities you can measure, averages. So here's a quantity, Kj. And since there are I outcomes, I equals 1 to n, for a given outcome, quantity Kj will have this value here. And the average value then is going to be simply for Kj here is just going to be the sum of K times the probability for that one for each I. So that's an average. So here's the problem you're faced with. Determine the probabilities such that the entropy is maximum given the knowledge you have about the system. So you would like to determine the piece that gives the maximum entropy given what you know about the system. And that is, as you hear, the Laplace principle generalized. Right, so this is what you do in porous media, because then I can do this. X is a configuration. That means a certain distribution of different liquids with different speeds, velocities in this plane here, in this representative elementary area. And the entropy is then the integral over all these configurations that are compatible with the hydrodynamics. Okay, this is entropy. And now we optimize this entropy, this Shannon entropy, knowing that first of all, the probability have to add up to 1. And we know the average flow rate through here. And we know the average wetting area, the area covered by the wetting liquid. That's what we know about the system. That we can go in and measure. So that's how we're going to proceed. And we're just following Janes here. Well, set up a Lagrange multipliers. Use that technique. So you produce a Lagrangian. So here's the entropy. And you have 3 Lagrange multipliers, one for the I mean that the p's have to add up to 1. I mean it is normalizability. And then you have one Lagrange multiplier connected with the average flow rate and one with the average area here, which is actually saturation. And you demand that this Lagrangian is at the maximum. And necessary but not sufficient condition here is that the derivatives with respect to the variables are all 0. So now we're going to go through this program and see what we get. So the first one is to take the derivative with respect to the probabilities, and this is actually a functional derivative, but that's fine. I mean, it's just, yeah. And that the Lagrangian derivative with respect to this parameter connected to the normalizability is 0. And that gives us, first of all, that probabilities are given in this form here. It's e to the minus q and a. And that was actually this one. And this one gives this here, and that's a partition function actually. This is a partition function. And you can sort of see that this is becoming a grand canonical ensemble type thing. It's very close to it, but it's in the 2 variables that we can measure, QP and the area. We continue. Let's see. Then we have the 2 other variables here. I mean, Lagrange multipliers, Q, lambda Q and lambda S. And by just going through the motions here, we find this expression and this expression. And the entropy can then be expressed in this form here. Now, if you look carefully, this is what we had. So I plug in this expression here, and I plug in this expression for the A here, and I end up with this. And you can see that this is actually Legendre transform. And Z here, the partition function had these lambdas as variables, and now I actually turned them into Q and A as variables. That's what this expression says. And then, now I'm going to define a new concept in porous media, and we call it agiture. This is sort of we have a competition, internal competition of what to call this thing. And at the moment, we're using the term agiture, but you'll see what it means. So here's the entropy expressed in QP and AW. Here is the partition log of the partition function, and here are the two other expressions here. And then I can write the partition function as E to something that looks like a free energy, but it's some sort of a flow rate. We don't know, have no idea what it is yet, but that's what we define. And I express now here this in terms of this Q. So I take this equation here and write it in terms of this Q, and I end up with this expression here, where I now used QP and AW here to do this. So I have now this expression here, and that comes from this Jane's calculation. So here's this Q, and that's actually the log of the partition function. I have no idea what it is in terms of physics. Here is the flow rate, and they are a function of the entropy and of this area. And here's entropy, and here are these area, and here are these Lagrange multipliers that we need to identify. So let's now concentrate on just this part here. This dq, d sigma, is 1 over q. Let me call that T, capital T, and plug that into here. And that means I'm actually doing a Legendre transform and changing this Q, P in sigma and A into Q, P of T and A. And what's T? Well, that's sort of a temperature. But, you know, when we were discussing temperature in this context here, I've done it in internal talks at home, and people get utterly completely confused. So I don't want to use the word temperature. So let's call it agiture, because it has to do with how much things are agitated. So agiture. Perhaps it's a bad expression, I don't know. But anyway, so agiture. Then we have another variable, which we call the flow derivative. So here is now, okay, so let me go back here, this expression here, and I've changed this into this QP of T and AW, and I'm left with this thing combined, and this. And that's what's written here. And I have dq, dA, I take this derivative here, this is 0 equals this, plus this is 0. Well, then I have this, and this quantity here, which is actually equivalent to the derivative of the average velocity over the saturation, wetting saturation, that I call mu. And this is what we call the flow derivative, and it is a sort of a chemical potential, but it has to do with the flow. I mean, this is flow in porous media. This is not thermodynamics. This is not statistical mechanics in the usual sense. So it needs new names. And when I have now defined this, I can write this expression in the following way. Okay. So this is this unknown flow rate. We don't know what it is yet. Here is the average flow rate in terms of the variable temperature, agiture, and here is the flow derivative. Now I want to make contact with the Euler theory. So I've just written this equation here is now written here again. And once again, this is the average flow rate in terms of the agiture and the average area covered by the wetting liquid. Here is the flow derivative, the equivalent of chemical potential, and this area here. I can now take out AP and make this into densities, and that means I'm dealing here with a velocity. And I do the same thing here. I can do this in a formal way, but I'll just demonstrate it like this. And when I've done that, I can write this equation as an unknown velocity. Here's VP, here's the average velocity, here is saturation, and here is this flow derivative, sits here. So this is a result of the calculation I just did. And now I can go back to the Euler theory, and I had the thermodynamic non-wetting velocity was given by the pore velocity minus SW times this derivative. And this is what I just had derived from Jane's statistics, statistical mechanics. You see, it's the same expression, which means I know what this is. This is in reality the thermodynamic velocity of the non-wetting liquid. Now we know what it is. The free energy is the thermodynamic velocity of the non-wetting liquid. That's the free energy here. And you couldn't have guessed this in a million years if you hadn't gone through this exercise. Now, if you go back to Euler theory and how it's set up, we had these constitutive equations, and they were, the velocity was a function of the gradient in the pressure. In Jane's statistical mechanics, you have the temperature, agiture and the saturation. Somehow they have to be related. We don't know yet. Delta P, the pressure gradient, is not this agiture. It is something else. We don't know what it is, but we'll figure it out. And then now look at the co-moving velocity. So here's the expression we had. So this was the thermodynamic velocity of the non-wetting liquid. This is the average velocity. And here is this derivative. I mean, this is the flow derivative. And here was the relation between the physical velocity and the thermodynamic velocity. And here is the co-moving velocity. And as you see, if this one is dependent on these two variables, you would expect that this one also using the same variables and the co-moving velocity using the same variables, the agiture and this flow derivative. And that means that if I now combine this equation and this equation, I end up with this one, which was the fundamental one from this Euler theory, this sort of thermodynamics equivalent. And you see now that it has the variables, and the variables we had no idea about because we can't get that at all from Euler theory. We now can see what are the proper variables to look at here. And if we now look at the co-moving velocity, we had measured this, and these are data from the literature, and you get these beautiful straight lines. and has this form is A plus B times this derivative. But at the same time, we have now found out that the Vm is a function of the adjector and Vp. And that means that these two are functions of this adjector and nothing else. But it remains to ask the question, so what about this? Why this simple form? Where on earth does that come from? We have some ideas where it comes from. And that comes from actually looking at the geometry of the parameter space we're dealing with here. And it would be much, it would go much too far to try to explain this here, but we are not 100% there yet to be able to show that it has to have this form, but we seem to be pretty close. But the amazing thing about this form here is that we look at a very wide range of parameters here, and it really seems to be following this form. It's a big mystery. I mean, life is beautiful when you have these kind of mysteries. But anyway, so let's now move away from the equilibrium situation and into a non-equilibrium situation. We've been looking at equilibrium thermodynamics in the plane, right? Steady state. We said steady state, and steady state is this situation where you basically have no structure except these clusters that are moving around on a pore scale, but you don't see macroscopically anything but local fluctuations, of course, but you don't see any. I mean, it should have the same adjective everywhere, for example, this thing. But anyway, let's say we have a patchy porous medium. By patchy, I mean that this is sort of a two-dimensional porous medium. I'm sending through a flow here in the z direction, and I have one patch here that has its own, let's say, wetting properties, have its own porosity. Here's another patch. Here's another patch here. Here's another patch. Here's another patch. So they're all different, but like this. And then you're sending through here this mixture of two liquids, immiscible liquids, and you get into a steady state. And in that steady state, you'll find in this patch here a given saturation, average saturation, and a given velocity, average velocity of the two wetting liquids. In this patch here, there'll be a different saturation, and there'll be different velocities of each fluid type. Same thing here, same thing here, and same thing here. This will have a different saturation from this, and this, and a different average velocity, velocity of the wetting liquid, and a different velocity of the non-wetting liquid from the others. But in time, as time is flowing, there'll be fluctuations, but basically it's going to find some sort of an equilibrium situation here, steady state. And the question is, so how on earth would you calculate what these are? Is there any way with this formalism here that we can actually do this kind of calculation? And the answer is yes. What you do is you go to non-equilibrium thermodynamics, because this is exactly the situation this is described for, constructed for. And these are the standard equations used in non-equilibrium thermodynamics. When you have two driving forces, you have the adjector, and look, let me just go back here. This is the x-axis, so this is orthogonal to the average flow direction, and the z direction is the flow direction. And what you find is, this is what, when you just transcribe the non-equilibrium thermodynamics equations, transport equations, they will have this form. So the changes in the average velocity and the saturation in the z direction, that's the flow direction, is related then to adjector gradients in the plane and flow derivative gradients in the plane, with 4 coefficients, transport coefficients. They are conductivities, you would call them conductivities. And the Ansage symmetry, which is actually quite a simple thing to measure numerically, experimentally in this system, you would expect this one to be equal to this one. And it's very important that one actually find this, but we are not there yet. So you have this, you combine them with, so you have this set of equations here, you combine it with this equation here, which is, tells you, you see it's the average velocity here and the saturation here that enters. So you don't know what to get these velocities, you have to go through this equation here. But this set here actually solves it. Whenever we try to do this in practice, but we can see in principle that it will do it. I mean, according to theory, this should work, perhaps. Anyway, we'll come to the point where I should summarize things now. We have constructed a statistical mechanics for immiscible two-phase flowing porous media based on the Jane's information theoretical approach. That was part one. We have introduced adjutor and flow derivatives as variables controlling the steady state flow. We have placed our 2018 paper, that's the one where we introduced the Euler approach, that introducing a pseudo-thermodynamics based on the Euler homogeneity theorem in a statistical mechanics context. So we're in the process of writing all of this up and testing these things out now on computationally, using lattice Boltzmann and using pore network modeling to do this. And we are in discussion now with experimentalists on how to measure these things. And the big thing is, how on earth do you measure the adjutor? The flow derivative is fine, that's no problem, but this one here is not so simple. And perhaps in order to understand that one needs to understand the relation between this and the gradients driving the system. The pressure gradient and the saturation gradient. We don't know that yet. So we are at the beginning, not the end, but I think we have the tools more or less placed now in place. And I guess that is the end of the talk. So let me just stop right here and let's go to the questions.
Okay, yeah, wonderful, Professor. We're well in time, and so thank you very much for the nice presentation. Okay, so now the floor is open for question and answer session. Those of you who have questions, please raise your hand in the MS Teams so that I can go one by one.
I have no question, but it was so nice talk, Alex. It was just amazing. The whole statistical mechanics you developed for this porous media. It's just wonderful. What I say. Yeah. Okay.
Yeah, I mean these are completely new ideas, and of course it's not so easy to explain this to certainly porous media people who come from hydrodynamics. It's much easier to discuss this in terms of statistical mechanics, which is the background we have here.
Yeah, it's basically statistical mechanics in a different context. What I see is it's fully statistical mechanical formula and all this is coming up in a very consistent manner. You have plugged in those things actually. Yeah,
I mean, I highly recommend this 1957 paper by Janes. It is it really is something to read. When you have a background from statistical mechanics, and I mean, it's a revelation actually to read the paper. It's so nicely written and it has so many examples of very different contexts where you can use this. So
I see.
I mean, for me, it was a great discovery, these papers by him.
So, any comments or questions, please?
I understand, I mean, what I'm explaining to you is, of course, this is basically one of the first times I talk about this. So, and there are many concepts here. So, I can see it's actually quite difficult to sort of puncture things here.
But it was in very consistent manner. You have, very starting with very simple points. You have started and build up the whole thing actually.
Yeah, the pace of your presentation is very good, actually. I mean, it's understandable. Many things, even for the non-experts.
Yeah.
Thank you, Alex. I have learned, I think from this lecture, I learned, statistical mechanics for a different context, completely from the scratch.
Yep. Okay. Well, thank you very much for the invitation then. And,
Okay, fine. So, no further comments or questions. Let us thank Professor Alex Hansen once again for such a nice presentation. And also, let me tell you that he is a honorary faculty of the Department of Physics. And for the next 1 year, he will be, in affiliation to us also. So we can approach him at any time for collaborations as well in the future. Okay.
yes.
So, with this concluding marks, okay, let me thank you once again, Professor. So hope to see you sometime, maybe when the COVID is away. Maybe we like to have you here in person.
Yeah, I'll come over as soon as I can.
Yeah, sure. Thank you
Yep.
then.
Okay. Yeah. Yep.
Okay.
Bye-bye
So
then.
I will talk to you tomorrow again.
Yes. Yes.
Sure.
Yep.
Bye.
Bye-bye.
Okay, bye.